So we saw that in the calculation of adiabatic flame temperature, we need the product composition. Okay, the product composition it should be determined properly in order to get accurate value of the flame temperature. Okay, so when you consider for example the methane reaction with air, so CH4 plus 2O2 plus 3.76 N2 giving complete combustion is assumed here, CO2 plus 2H2O plus 7.52 N2. So now here due to high temperatures the major products dissociate. So the dissociation reactions we have seen that CO2 dissociates to CO plus half O2, H2O dissociates to H2 plus half O2. Okay, so the product mixture will have CO, H2 and O2 in addition to what we actually assume as a complete combustion. So if you see the product mixture, it will have some moles of CO2, say A moles, so B moles of CO and C moles of H2O, D moles of H2 and this E moles of O2. But you can also add several species in this and you can extend the list as we want. So, but to determine this unknowns here, the number of moles A, B, C, D, E, you need 5 equations, but you have by carbon, hydrogen, oxygen balance, you have only 3 equations. Okay, so 2 more equations are required. So these 2 more equations we actually derive from equilibrium equations. So in fact, the CO2 dissociating to CO plus half O2 or H2O dissociating to H2 plus half O2, these 2 equations are called equilibrium equations. They are molecular level equations. We have already discussed about the dissociation. So it's a molecular level dissociation. One CO2 molecule dissociates to CO and O2. So now the equilibrium reactions should be used. These 2 equations should be used somehow, and the 2 more equations which are required to complete the set of equations should be produced. For example, 3 atom balances will produce 3 equations. So 2 more equations from these 2 equations, for example, can be generated, so that 5 equations can be generated with the 5 unknowns A, B, C, D, E, so that you can solve that to get the product information. But please understand that this product, the number of moles of this is dependent on temperature itself. So that is the main problem here. So that means that your iterative process becomes more complex. So previously we saw that for adiabatic flame temperature, even if the product composition is known, then we have to first guess the temperature and find the HP, compare it with HR and see whether they are equal, or else you have to re-guess or iteratively solve this temperature. But in this case what happens, you have additional step. So you first again guess the value of product temperature Tp, then you calculate equilibrium products A to E. You have to calculate by using 3 atom balance equations plus 2 equilibrium equations like given here, and then you calculate the equilibrium products and calculate HP, the enthalpy of the mixture. If it is same as that of HR or the difference between HP and HR is negligible, then it is fine. Or else if it is not negligible, then you have to assume another value of Tp. Then the additional step is again you have to calculate the equilibrium products at that temperature. That means this equilibrium products are dependent on temperature basically. So for that you need what is called second law concepts. So that is what we are going to see further. Chemical equilibrium. So this chemical equilibrium basically allows us to determine the equilibrium products as a function of temperature and pressure. Okay, now consider this equation, dissociation of CO2, which is one of the major products. Say when the temperatures of 2000 Kelvin this order comes, then you can see the dissociation of CO2 occurring. At lower temperatures it may not occur. Okay, so this equation is a reversible equation. So CO plus half O2 can form CO2. CO2 can dissociate to form CO plus half O2, and based upon the temperature, either the forward reaction, which is dissociation, can occur or the backward reaction can occur. Okay, so even you maintain the temperature as constant, then to some extent these reactions will occur. Okay, the rate at which these reactions occur, the forward and backward, will be the same at a given temperature. So that you have to find. So based upon temperature, the extent will be varying. Okay, now if you now you fix the temperature and pressure of the combustion chamber, which may be a system or control volume, then based upon this some amount of CO2 will dissociate, and the reverse reaction also will be frozen. Both will be at the same rate, so that you get in the products all the three species in some proportions. Okay, so how to find the proportions at a given temperature and pressure? So that for that you need second law concepts. Okay, now let us assume that alpha kilomoles of CO2 dissociate. See, when alpha kilomoles of CO2 dissociate, so CO number of moles of CO formed is alpha, and alpha by 2 O2 will be formed. So initially, if CO2 is say 1 kilomole, then in the mixture you will get 1 minus alpha kilomole of CO2, alpha kilomole of CO, and alpha by 2 kilomoles of O2. So this is the mixture you have. What is alpha? This alpha is determined by at a given temperature and pressure. So this is as a function of temperature and pressure, it will vary. So for a given temperature and pressure, this may be evaluated by using the second law concepts. Okay, now an important property which is derived using the second law is the entropy. Okay, so entropy basically will tell about the feasibility of a process, whether the process can occur or not, and the direction of the process, direction of flow, and several things. It is very useful, and for irreversible, calculating irreversibility, etc. So entropy is a very important property. In this case, we are going to use entropy to derive few more properties which are going to be helpful for us in determining the chemical equilibrium. Okay, so entropy is very important property which is going to be used in deriving additional properties. Okay, so how to do that? Now let us just see how entropy of a species is first calculated. Entropy of a species depends both on temperature and pressure. Okay, unlike enthalpy, which is only dependent on temperature, because we are assuming the mixture of reactants or products to be ideal gas. So for ideal gases, enthalpy is only a function of temperature. On the other hand, entropy is a function of both temperature as well as pressure. Okay, so it has a value at standard temperature or reference temperature 298 Kelvin, and its value increases due to increase in temperature from 298 to any temperature T. So where we are going to fix the system or control volume 2. Similarly, if the it has a certain value at atmospheric pressure, but as the partial pressure of the species changes, so if the total pressure of combustion varies, the partial pressure of species also will vary. So depending upon the partial pressure of the species, the value of entropy will change. So entropy depends both on temperature and pressure. So we can write the specific entropy in molar units. So joule per kilomole Kelvin we can write as for any species I. So Si for any species at a given temperature T, and the partial pressure of the species is Pi. Okay, it is not equal to atmospheric pressure, so Pi. So even if the combustion occurs at atmospheric pressure, since the partial pressure of the species is different than the atmospheric pressure, you will have a pressure dependence. Okay, so now you split the term into two basically. So this is the entropy, standard entropy value of the species I. Okay, so it is calculated at the reference temperature of 298 Kelvin and atmospheric pressure P naught. Okay, you can put P superscript 0 or P subscript 0. So both represent atmospheric pressure. T reference is 298 Kelvin. Now, if the temperature is different than the reference temperature, then you have to integrate this. So this is got by integrating Cp dt by T from Tref to T. Tref to T, you will get the change in entropy due to temperature change. So that should be added to this. Okay. Similarly, pressure, as I told, pressure is different than the atmospheric pressure or any operating pressure. So operating pressure may be P, it may not be equal to atmospheric pressure always. So partial pressure will be different. So since the pressure is different than the atmospheric pressure P naught, so this is the pressure dependence minus Ru natural log of partial pressure of the species divided by the atmospheric pressure. So these additional terms are added to get the entropy of a particular species at a particular temperature T and its partial pressure Pi. Now the first two terms are clubbed as this, okay, entropy of the species at the given temperature T but at atmospheric pressure, then add the pressure dependence here Ru ln Pi by Po. So this is the way you calculate the entropy of a given species at a particular temperature and particular partial pressure. Okay. Now once you know the entropy of all the species, then the entropy of the mixture is calculated at any temperature. So it may be a flame temperature or any other temperature, and the operating pressure is P. Now you please see that this is the total pressure in which the combustion chamber is operated. When you sum up all the partial pressures of species, you will get the total pressure. So now the entropy of the mixture at the temperature and the pressure is nothing but entropy of the particular species here multiplied by the number of moles. The same thing what we do for enthalpy, you do that. So in this case, if alpha 1 minus alpha moles of CO2 is present, 1 minus alpha of entropy of CO2 calculated at the temperature. Similarly, alpha times SCO, similarly alpha by 2 times SO2. Okay. So you have to calculate. Please understand that when you do the calculation, pressure should be partial pressure of the species. So you calculate the entropy of the mixture. So now once you know the entropy of the mixture, okay, when you have isolated system or a control volume, isolated control volume, there is no heat interaction or work interaction. Especially when there is no heat interaction, entropy cannot change. So entropy can change either due to heat interaction or reversibility, any irreversible process occurring in the system. So it will change, or if heat is transferred to the system, it will change, or if heat is rejected by the system, it will change. So due to heat interaction or irreversibility, entropy can change. When I say it is isolated system, that is no heat interaction. So entropy cannot change due to heat interaction, but it can change only due to irreversibility. Okay, but when there is an irreversibility, entropy always increases. If there is no irreversibility, entropy will be same. So isentropic process is nothing but entropy remains constant when there is no irreversibility. So either ds can be greater than 0 if there is any irreversibility. Obviously in this case reaction is going to take place, chemical reaction, it is highly irreversible. So we expect ds to be greater than 0. When the equilibrium condition prevails, the reaction stops. That means there is no irreversibility anymore, and there is no heat transfer also. In that case ds will be equal to 0. So that is the chemical equilibrium condition, ds equal to 0. So that means that at that particular point S mix should become maximum. Okay. So this is the thing. So if you take we want to evaluate the equilibrium condition, you should see that the entropy should be at its maximum value. Okay. Now entropy cannot be always used for our calculations. See, for example, when I say this, when I say here ds equal to 0, that is something you should write ds at a constant u, constant v and constant mass equal to 0 for equilibrium. That means internal energy is constant at a given internal energy and volume and mass, this ds is equal to 0. So we cannot find the condition like this everywhere. Okay. So actually what happens is, when you assume a constant volume process, when a constant volume process is in equilibrium, if entropy is specified to be constant, S is constant, then internal energy assumes a minimum value. Okay. On the other hand, if internal energy is specified to be constant, like this, constant internal energy here, then ds will be equal to 0. That means entropy assumes a maximum value. Okay, but we cannot say internal energy to be a constant. It is not possible for us to make internal energy to be constant. In fact, it will not be. So if neither S nor U are constant or is constant, then what happens? Then a quantity called U minus Ts will assume a minimum value. Minimum value. Please understand, it is not a maximum value, it becomes a minimum value. This quantity U minus Ts is called a free energy. It is called Helmholtz free energy, and it is given a letter A, capital A. Do you understand? So when there is a constant volume combustion occurring, if the quantity U minus Ts, which is the Helmholtz free energy A, assumes a minimum value, then equilibrium is said to be prevailed. Chemical equilibrium is attained. Okay, now for constant pressure process, you define enthalpy like this: H equal to U plus PV. Correct? It's a derived property. Okay, even though it's derived from constant pressure process, it is a property at a state point, basic state function. Now, similar to that, you can derive Gibbs free energy. Okay, that is G equal to Gibbs free energy is G equal to H minus Ts. So here U plus PV minus Ts. So that is the G. So you can derive the G just like how you derive the value of H. So now this Gibbs free energy is used for constant pressure process, and this Gibbs free energy attains a minimum value at the equilibrium of a constant pressure process. Okay, so similar to constant volume process where Helmholtz free energy attains a minimum value, constant volume process, in a constant pressure process, Gibbs free energy attains a minimum value at equilibrium. So this is what is important. So as I told you, we are deriving two more properties. One is called Helmholtz free energy corresponding to a constant volume process, or Gibbs free energy for the constant pressure process. Both involve entropy in it. So Ts, okay, so H minus Ts for Gibbs free energy, and U minus Ts for the Helmholtz free energy. So now, so entropy, since entropy is involved in this, Gibbs free energy is a function of both temperature as well as pressure, because you can see H is a temperature dependent only for ideal gases, but since S is dependent on pressure, G will also be dependent on pressure. Now, so for instance, if the mixture entropy and the mixture Gibbs free energy are plotted like this, okay, here in this plot, in the y axis I plot mixture entropy and mixture free energy, different scales, okay, different scales I plot, and the extent of reaction is plotted in the x axis, extent of reaction. Okay, so that means that if I am saying just I am plotting the number of moles of CO2, 1 minus alpha, correct. So that when I say it is 1, see it varies from 0 to 1 for example, okay, then the plot goes like this. So now you can see that the entropy increase, when the entropy is showing increasing trend like this, that means that reaction, a particular reaction is taking place, either a forward or backward reaction. When it reaches the maximum, you can reach the equilibrium condition. So S mix attaining a maximum value, or ds equal to 0, that represent the equilibrium condition. This is the number of moles of CO2 at the equilibrium, 1 minus alpha E. So, okay. Now similarly, a backward reaction can occur starting from here and it may reach a maximum value. So here equilibrium is said to prevail. Now this is for a given temperature T and pressure P, total pressure of the thing is P. So please understand that, okay. So when you vary the temperature or pressure, this maximum value will shift. That means 1 minus alpha E value will shift according to the pressure and temperature. Similarly, when you take G, when G shows a decreasing trend, that means that some reaction is taking place and it reaches the minimum value where the equilibrium condition is reached. Okay, this is for the reverse of the reaction, and this. So both can take place. So for example, if you have a piston cylinder arrangement in which a water and water vapor is there in this. Okay, this is liquid water. So this is water. So fully this is water, this is liquid, and this is vapor. So in its own vapor, liquid water is prevailing, and it is a piston cylinder arrangement, so that pressure is maintained at a whatever value you want, so P. So now the temperature is T. So what happens now, under this condition, the mass will not change, the mass is remaining constant. So constant mass, temperature is constant, pressure is constant. That means that the Gibbs free energy should be constant. That means the Gibbs free energy of the liquid water will be equal to the Gibbs free energy of the vapor. that is called phase equilibrium. Okay. So that means the dg totally is equal to 0. Okay. So we can write at equilibrium dg at a given temperature, pressure and the mass will be equal to 0. Okay. So this is the phase equilibrium. In this case, phase equilibrium defines the condition that the number of molecules leaving the liquid to the vapor will be equal to the number of molecules leaving the vapor to the liquid. So that is a dynamic system. See, you can see that the vaporization occurring is at the same rate as the condensation, but the number of moles or the energy level of liquid and the energy level of vapor is preserved in terms of Gibbs free energy. So similar to that, the forward reaction can occur when there is a decrease in the Gibbs free energy, reverse also can occur, but once this minimum value is reached, okay, there equilibrium prevails. So for a given temperature and pressure, there is a definite equilibrium value for the products, that is 1 minus alpha E for CO2. That means the others will have alpha E CO and alpha E by 2 O2. Okay. So this is the equilibrium value. So that is dependent on pressure. So the condition for that is dg should be equal to 0 at a given temperature and pressure. That is what we have to. So how to do that? So once you know, so you know now how to calculate enthalpy, you know how to calculate entropy. So combining this, you can calculate the Gibbs free energy. Okay. Now Gibbs free energy change. So we are interested in the Gibbs free energy change dg, that should be equal to 0 for equilibrium. So how to calculate dg? Okay, let us first take a non-reactive system. Okay, so number of moles does not change of any species does not change. If the number of moles of species does not change, we do not even require to get that into the equation. So G equal to H minus Ts, that means dg equal to dH minus Tds minus SdT. So this is known to you. So now you can use the Tds relationship. The Tds equal to dH minus Vdp. Okay. So use this equation and you get dg equal to minus Vdp minus SdT. So this is the equation which we can use to find the change in the Gibbs free energy for a non-reactive system. Okay. So now you can say that G is a function of P and T. So dg is nothing but dou G by dou P at constant T dP plus dou G by dou T at a constant P dt. Now you can see that dou G by dou P is nothing but, so now please n is also constant here. N is also constant here. So just writing n there. So dou G by dou P at constant T is nothing but minus V. So this is nothing but minus V. Similarly, dou G by dou T at constant P is nothing but minus S. From this you can equate this and see. Okay. Now if there is any reaction or any phase change, for example, even in a phase change or any reaction, when the number of moles is going to change, then we have to add few more terms here. See, for example, for reactive system, let us consider reactive system n1 kilomole of reactants. So let us group the reactants into one species, say reactant species, and product into product species. So when reactants are consumed, product will be formed. So let n1 kilomole of reactant be present, n2 kilomole of product be present. So now what happens? The n1 and n2, they are not going to be constant. So initially n1 may be some number and n2 may be 0. So now as the reactants are consumed, n1 decreases and n2 increases. Okay. So that is what you have to take into account here. So now the change in the number of moles of the reactants is dn1, change in the number of moles of products is dn2. Now you have to suitably multiply. See, since here we have multiplied what? So minus V corresponds to dou G by dou P at constant T. Okay. Similarly, mu1 here will correspond to some change, partial change of G with respect to n1, correct, when temperature and pressure and N2 is constant now, because there are other variables. See, once one variable varies partially, if you want to differentiate, other variables should become constant. Okay. So, mu1 is nothing but dou g, said mu1 is nothing but dou g by dou n1, correct, dou g by dou n1 when pressure, temperature and the product, this is remaining constant. So, this is called a chemical potential. How the free energy varies with respect to the number of moles of the reactant, that is a chemical potential, or it is called partial molal Gibbs function with respect to a particular species, reactant species for example. So, this is the way you write this. Similarly, mu2 will be equal to dou g by dou n2 when pressure, temperature and n1 are held constant. So, now that into dn1 will give you the, so mu1 into dn1 will give you the change which happens when there is a change in the number of reactant species. Similarly, mu2 into dn2 will give the change in the Gibbs free energy when there is a change in the n2 or the product species number of moles. Okay. Now, at a constant pressure and temperature, this term dp and dt goes to 0. So, you can write this like this. So, I am just now changing mu1. So, this is nothing but I am saying this is g1 like. So, dou g by dou n1 partial molar change I am writing as g1 overhead bar. You can also leave overhead bar. So, g1. Similarly, this is g2. So, now I can say that dg is g1 times dn1 plus g2 times dn2. So, how to calculate these g's? That is what is going to be the next step. So, let us now calculate the value of g1 and g2 bar. Now, for that what we try to use is the definition of g, correct. So, g at any temperature T and P can be calculated as H at the given temperature and pressure. For ideal gases, pressure dependence will not be there for enthalpy. So, H at T you can say minus T times S of T comma P. Okay. So, now entropy will have will be dependent on both temperature as well as pressure. Now, let us try to do for given species, then we can apply the mixing rule for this. So, take the ith species which is at temperature T and its partial pressure is Pi. Okay, ith species has a partial pressure of Pi, that is Xi into P. So, that enthalpy of the species is Hi of T, which is nothing but the formation enthalpy HFI at 298 Kelvin plus delta Hi at T. Okay, that is the enthalpy sensible enthalpy. So, that we can calculate, and you know how to calculate this. So, Hi of T, that will be the enthalpy of the ith species at given temperature. Now, coming to the entropy, entropy has two terms, Si of T comma P naught. This means this Si, the ith species, it is calculated at the temperature of T, but atmospheric pressure P naught, and the pressure dependence comes by the second term minus Ru natural logarithm of Pi by P naught. So, that will be the pressure dependence of this particular term. So, when you combine this, you can see that T times Si of T comma P naught minus Ru ln of Pi by P naught, that will be the entropy. So, entropy into temperature. Now, let us gather the first two terms Hi of T minus T into Si of T comma P naught. So, these two terms I try to gather and put it as Gi of T comma P naught. This is nothing but the Gibbs function of the ith species at the given temperature T calculated at atmospheric pressure P naught. So, that is the first term. Okay, then pressure dependency of the Gibbs function, which is arising due to the pressure dependency of the entropy, that will be given in the second term Ru ln Pi by P naught into T. So, that is the second term which is coming here. So, we can write when you try to calculate the Gibbs function for a particular species at a given temperature and its partial pressure, we split that into two terms, Gi of the particular species, that is species I, Gi at T comma P naught. Okay. which is calculated at atmospheric pressure, plus the pressure dependency coming due to this second term RUT ln of PA by P naught, that is it. So, now you can use tables which directly give the Gibbs function of the particular species as a function of temperature and use calculate the first term, or you can take the enthalpy of the calculate the enthalpy of the ice species at a given temperature and use the formula H minus Ts to calculate. So, entropy also you can take from the tables and you can do that to calculate G. So, either way you can take the value of G at a given T, but calculate the atmospheric pressure P naught. And the second term is obvious, you can know you know the mole fraction of the particular species. From that you can calculate the total pressure. So, mole fraction into total pressure will be the partial pressure. So, use that to calculate this. So, both temperature and pressure controls the value of G. Okay. Now, for constant volume process you need partial molar Helmholtz function A. So, how we calculated internal energy? By first calculating the enthalpy, we try to calculate internal energy. So, use the definition of the enthalpy H equal to U plus PV. So, we calculated U as H minus PV. Similar to that, I calculate the Helmholtz free energy or Helmholtz function as a function of Gibbs free energy and PV here. So, I can write AI, which is the Helmholtz free energy molar based at a given temperature and partial pressure of the ith species will be equal to Gibbs function, which I calculated above at a given temperature and the partial pressure, minus Pa into V. For a constant volume process, this V is constant. So, we can calculate the Helmholtz free energy. So, let us illustrate this for Gibbs free energy, then we can use the Gibbs free energy to calculate the Helmholtz free energy, like we first calculate the enthalpy, then we calculate internal energy. Okay.